Hello everyone, welcome to my channel Dr. Vijay SSOC. In this video, we are going to discuss about one-dimensional and two-dimensional HOESY NMR spectroscopy and their importance in structural elucidation of fluorine compounds. By the end of this video, you will understand that 1D or 2D HOESY NMR, which one is easy to perform and which one is faster. And you will understand that when you need to perform HOESY NMR for your compound and how to interpret them. So let's start this video. HOESY stands for Heteronuclear Overhauser Enhancement Spectroscopy. So it is an NMR technique used to investigate spatial proximity between two different nuclei. So there are different type of HOESY. For example, 1H-13C HOESY NMR, 1H-19F HOESY, 1H-31 phosphorus, 1H and 15 nitrogen HOESY. In this video, we are going to focus mainly on proton 19F HOESY NMR spectroscopy. So this spectroscopy measures the heteronuclear overhauser effect. If you remember, in my previous video I discussed about NOESY and COSY, and in NOESY this it measures the nuclear overhauser effect, and here it is the heteronuclear overhauser effect. So the principle is exactly the same, because the dipole interactions between the two different nuclei which are in close proximity is measured by the HOESY NMR. And let's take the example of proton and 19F HOESY NMR. So if fluorine is close to the proton, then you will see the cross peak in the 2D spectrum. And but in case of NOESY, the difference is only you see only proton-proton interaction through the space, and here is the interaction through the space but between proton and fluorine in case of proton-fluorine HOESY NMR spectroscopy. But the range is same, 5 angstrom, maximum 5 angstrom you can see the interactions, and this is does not connected to the bond. So this interaction take place through the space. So why it is essential? Unlike COSY NMR method, which is completely depend on the bond connectivity, and you can only measure up to the 4 bond coupling, but 5 is impossible to see. Therefore, COSY can't be used to see the long range coupling or long range interactions between the protons. But in HOESY, there is no non-bonded spatial interactions between the nuclei. Therefore, you can see the long range interactions, or we can say that overhauser effect, and therefore it is useful for complex structure elucidation. It is also useful to provide the structure elucidation of fluorine containing compounds where NOESY failed to provide the full picture. We will see the example in the next slides, and then we will understand. So let's take the practical example of nucleophilic aromatic substitution reaction, which is called in short as SnAr. So this compound, which is 2,4-dichloro-5-trifluoromethylpyrimidine, when reacted with amine, this R could be methyl or any other alkyl having other hydrogens. When reacted with dipia in DMSO at 100 degrees Celsius, then you get mixture of products. One is 4 substituted product and another is 2 substituted product. So this 4 substituted product is slightly major in amount as compared to the 2 substituted product. This chloro, 2-chloro and 4-chloro have comparable reactivity. We will understand very soon why it is so. So let's do the SciFinder search and see what is results, what we see that. So if you do the SciFinder search, you will see that the reaction of methylamine with this compound gives you 4 substituted product as a major compound, and you can see that except this reaction condition, you see other reaction condition where diisopropyl ethylamine in ethanol THF is giving 53% yield. Here is also 53% yield. In this patent they don't explain anything, so patent does not have rules like the articles or journals. In journals you have to explain each and every details, but in patents you don't need to explain anything. So you can see that the yields are 50% in most of the cases, because as I told you, the other product is to substituted. But when you will have to do this reaction in your lab, so you have to characterize which one is 4 substituted and which one is 2 substituted. So let's move further. If you see 2,4-dichloropyrimidine, in this case, if you do these same reactions, then you will get exclusively 4 substituted product, or we can say predominantly 4 substituted product, because 4-chloro is highly reactive as compared to the 2-chloro. To understand the reason, you can read the heterocyclic chemistry book written by Jules Miller. So this chloro is more reactive. But when you put electron withdrawing group para to these two chloro substituted, then this two chloro also become reactive towards nucleophilic aromatic substitution reactions. And these electron withdrawing group could be CF3, nitro, or cyno. And then the reactivity becomes almost comparable. But this compound will always be slightly major in amount as compared to substituted product. Now question comes that, so yeah, so here is just I try to say that 4 chloro and 2 chloro reactivity is almost same due to CF3, presence of the CF3 group. So now let's move forward. So you will have mixture of product 4 substituted and 2 substituted. Now the question arises how to differentiate between these two compounds. If you take 1H NMR, then you can't differentiate because there is a one proton from the pyrimidine ring and amine hydrogen, and let's say proton from this alkyl part. So the if you see this structure, it will be the same. You can't say that what will be the ppm of this proton and what will be the exact ppm of this proton. So we don't know exactly what ppm it will show in NMR. So the NMR's pattern will be same. So you can't distinguish. So we rule out this method. So what about 2D COSY NMR? There is no Wissner protons. So you will not see any COSY interactions in this case, in this molecule. But what about 2D NOESY NMR? You can do 2D NOESY NMR, and in this case you can see probably you can see the amine proton cross peak with the ring proton, but you will see in the 4 substituted product as well. So 2D NOESY NMR also failed to distinguish these two compounds. These two compounds can be distinguished only by uh, proton fluorine HOESY NMR. So first we will talk about 2D HOESY NMR, and then we will see 1D HOESY NMR. So let's move forward. So in case of 4 substituted product, if you have this product, then you will see uh, 2 cross peak. First, because of the CF3 will interact with this pyrimidine ring proton to show the cross peak in the 2D NMR. And another cross peak will arise by the interaction of the CF3 with amine proton. If this R has proton, then also you can see the third cross peak by the interaction of this fluorine with these alkyl protons. But if you have two substituted product, then you will see only interaction of the CF3 fluorine to the ring proton. But due to the long distance, you will not see the interaction of this amine proton with the CF3, and hence you will not see any other cross peak due to this interaction. So this way you can differentiate between 4 substituted product to from 2 substituted product. Now it is very important to understand how 2D 1H-19F HOESY NMR looks like and how to interpret them. So let's take the example of compound, and this compound is published in Organometallic Journal, published by R. Tom Baker Group. And this is the 1H NMR of this compound, and this is the fluorine NMR. They put fluorine NMR on the x-axis and 1H NMR on the y-axis, but usually it is reverse. Proton we keep on the x-axis and fluorine we keep on the y-axis, but it doesn't matter. Let's see. So it was important to assign the configuration, or we can say the geometry about this around this double bonded carbon. So it was very important to perform this 2D 1H-19F HOESY NMR. So this is the CF3 signal and this is the fluorine from this carbon, and they observed that very strong heteronuclear Overhauser effect between this CF3 fluorine and this cyclopentadienyl proton, due to which they observed the cross peak, and this indicates that CF3 is in close proximity to the cyclopentadienyl ring. But if you see this fluorine, there is no cross peak arising due to these interactions, which indicates that this fluorine is far away from this cyclopentadienyl group. But they observe that this fluorine is interacting with the uh, phenyl group protons, which indicates that this fluorine is in close proximity to this phenyl ring, and hence they assign this geometry to this compound and they rule out this possibility. So you can see that how this HOESY and 2D NMR is highly important. Now, I hope you understand how to interpret 2D HOESY NMR. Now let's move back to the our problem. So as we said that we can distinguish this compound by 2D. Now we can say that this compound can also be distinguished by 1D HOESY NMR. And 1D HOESY NMR is faster than 2D HOESY NMR. So it saves your time. That's why you can perform 1D 1H-19F HOESY NMR to save your time. But you can distinguish by either way. So how it will help, I will show you. So we have only one CF3 group. So when you irradiate the fluorine of the CF3, and if you see the intensity of the NH or R protons increased, it means you have four substituted product. But on irradiating the fluorine of CF3, if you see only ring protons intensity increasing and there is no HOE, HOE stands for heteronuclear Overhauser effect. If you don't see any HOE between this amine proton, it means this this is two substituted products. So once again, I will tell you what I am trying to say. In 1D proton fluorine HOESY NMR, you have to irradiate the CF3 fluorine signal. On irradiating the CF3 fluorine signal, if you see uh, increase in the intensity of the amine proton or R protons, it means this is in close proximity. This substitution is in the close proximity. But if you don't see any kind of increase in the intensity of these amine proton, then it means it is two substituted product. I know you are still confused. So let's see how 1D proton fluorine HOESY NMR looks like. So I took example from this website geol.com, and you can see this is the structure of the compound, and this proton I just put like this. This is, let's say this is hydrogen A. This is the NMR 1H NMR of this compound, and this is the 1H-19F one-dimensional HOESY NMR of this compound. So you can see that when they irradiated this fluorine, they observed that intensity of this proton, which is, you can see proton NMR, you can see that this comes around 8.67 ppm. You don't see any other signal in this one-dimensional proton fluorine HOESY NMR. Only you see the intensity of this proton, which indicates that this CF3 is in close proximity to this hydrogen atom. Okay, if this example is not enough, let's move to another example. And now I'm sure you will understand how to interpret 1D proton fluorine HOESY NMR. Okay, so here is the example. This is the NMR of this compound. And let's say we know this signal belongs to which proton through this splitting pattern. So A is belongs to this proton, and this is the signal from B proton, and this is the signal from the C proton. And this is the fluorine NMR. And there are two fluorines, so but we don't know which fluorine is this and which fluorine is this. So uh, when we irradiate this fluorine, which is around 100 minus 130 ppm, we see the increase in the intensity of the C proton. But A and B are very slight increase in the intensity. So it means this fluorine is close to the C proton. Therefore, we can say that this signal is coming from this signal is coming from this fluorine. Okay, when they selected this fluorine and irradiating of this fluorine, they observed that very poor increase in the intensity of the other signals. You can see that very slight increase in the intensity. So it means this signals, which is around minus 90 ppm, is belongs to 2-fluoro. I hope that 1D proton fluorine HOESY NMR is clear to you. Thank you very much. If you find this video very useful, please like it and subscribe to my channel.